This is Sholey Physics Combination Circuits Edition. Today we're going to look into a combination of a series and a parallel circuit. Here I've got a 2 ohm resistor in a funny combination with a 5 ohm and 10 ohm resistor. Now to just use the terminology well here, the 2 ohm resistor is not in parallel with the 5 ohm or the 10 ohm, but it's not really in series with them either. See, a series would indicate it's on the same branch as these two, but kind of have the 2 ohm resistor and the wire leading up to this junction here. It's on a different branch than these two. So you'll see that the flow of electrons through the battery are not the same as the flow of electrons through the 5 ohm and 10 ohm resistor, but it is the same through the 2 ohm resistor, the 2 ohm light bulb there. I like the light bulbs. They're a little more interesting than those boring resistor little things. So I'm using light bulbs. They shine. You can also see that kind of get a sense for which one's brighter than the others. So, all right. So moving towards the point here. This is called a combination circuit because there is a parallel section, and this parallel section is in series with the 2 ohm resistor. I'll show you how that works out here in a moment. So if we were to turn this into a circuit diagram, it will look a lot like this. This is one version. We've got the 2 ohm resistor, the 5 ohm, and the 10 ohm. All right, and so if we're to try to find the equivalent resistance, what we're going to try to do is turn this into a single resistor. Okay. So that's our goal here. What is the equivalent resistance of all those resistors together? And the last thing is, what is the current, the flow of current going to be? So these are the two things we're going to try to find out here. We can use our series resistor equation. We can use the parallel resistor equation. We can also use Ohm's law, V equals IR. So we're going to use those. That's our toolbox right there. So where do we start? Well, if we try to add 2 to this, we run into a problem because we don't know what that is. So let's look at this circuit in terms of like pieces. If we're an electron and we go out of the battery here, we're going to pass through this resistor first, right? And then we're going to have to pass into this section. So there's like 2 different sections of the circuit here. We've got the 2 ohm and then these parallel resistors. So what we're going to do is find the equivalent resistance of the parallel section first to turn it into a circuit with 2 resistors. All right, so we're going to make this look a little like, well, we want it to have a 2 ohm and then replace these 2 resistors that are in parallel with whatever their equivalent resistance is, the equivalent resistance of that parallel piece. So we're going to turn it into this first before we turn it into that. All right, so do you see the flow here? We're going to determine the parallel resistance and then add it because series resistors add. All right, so my first task is I'm going to find the equivalent resistance of just the parallel resistors, and 5 ohms is in parallel with 10 ohms. But do you see there's not a 2 ohms isn't on a parallel path? Got to keep that in mind. You don't want to go 1/5 plus 1/10 plus 1/2. This is not a parallel path to these two. You can go from, let's say, point A here to point B, either through the second resistor or through the third resistor. But there's this other, I'll call it point C out here. Right? It's along a different path. So let's leave that one alone for now. So just focusing on those parallel resistors, we're going to have 1/5 plus 1/10. And if you weren't able to work out that fraction math before, this will be a good example for you. So this is not going to be 1/15. We need to find a common denominator first. You got to, of course, plug them into your calculator, but let's make sure we know that fraction math. It should be a simple thing. And I think you're going to be reminded here in a second that it's not very hard. So a common denominator, well, what does 5 and 10 both go into? They both go into 10. 5 goes into 10 twice, so 1/5 is the same as 2/10. And 10 goes into 10 once, so we're going to keep it as 1/10. Okay, so 1/10 plus 2/10 is 3/10. There it is. So we get 1 over the equivalent resistance of those parallel resistors. I'm going to move it down here a little bit, finish our math problem, equals 3/10. Surely flip method, flip. All right, this is the ratio flip. 1 over RE is equal to 3 over 10 as RE over 1 equals 10 over 3. Okay, so those ratios are the same. You could also cross multiply. 3 times R equals 1 times 10, and then you have to take 10 divided by 3 anyway. So turns out 10 thirds, and that is 3.33 repeating ohms. All right, so there we have the first segment here. And whenever I get an equivalent resistance like 3.33 ohms for a piece of the circuit, I like to write that in there. Usually if I don't have enough space, I'll write 3.33 right in here, but that'll get a little crazy. So I'm going to write it right above here, 3.33 ohms, circle it. Okay, so this segment is 3.33 ohms. To get it back to this step, okay, what we've just found is 3.33 ohms. So now, what is going to be the equivalent resistance of the entire circuit? We now have a 2 ohm resistor in series with an equivalent of 3.33 ohms. So we now have 2 series resistors, and our overall equivalent resistance is going to be the equivalent resistance of the parallel piece plus the 2 ohms. So we're going to have 3.33 plus 2 ohms, which is 5.33 ohms, 5 1/3. Okay, so there it is. There's the equivalent resistance. That's our number one goal. Our second goal was to figure out what the current is going to be. Now this one's not going to be a nice easy number, because to find the current, we're going to plug it into V equals IR. It's easy to find, but just not easy to calculate in your head. Our voltage value is 15, and our R is 5.33 repeating. Right? So this part is kind of easy to solve. Plug them both in, divide both sides by that resistance. So as you can see, 15 divided by 5 is 3. So we're going to get a value a little bit less than 3. And when you calculate that out, it comes out to 2.81 amperes. There's the current flow. All right. So that's an example of a combination circuit, or first, it's probably the easiest one to look at. But just to recap, what we did was we found the equivalent resistance of the parallel piece, and we added that because that's in series to this 2 ohm resistor, and then calculated the current flow, the I, through that battery due to all those resistors together. All right, let's do one more example here. Okay, we'll get this one a little bit more involved. What if we have two resistors, then one? Let's try this out. And I'm going to get even crazier, because this should cover all the bases. Whoa. Don't tune out. This will be worth it. And I'm going to try to make it not take too long. So let's go like that. We'll keep it as 2. We'll try 3 ohms, 3 ohms, 3 ohms. All right, then down here, let's do a 2 ohms, 3 ohms, and 10 ohms. All right. Now what I hope you'll see from this, let me get 20 volts. What I hope you'll see from this is a couple of ways when you're looking at these circuits and you notice a pattern. This might actually speed you up and help you get through your own problems that you work problems and circuit problems that you're working through. So here, look, we've got 1, 2, 3, 4 different sections of the circuit. So what we're going to try to do is find the equivalent for this piece, find the equivalent for this piece, find the equivalent for this piece. And once we have those equivalents, they're all in series, we're going to then be able to add them all up and finally figure out the current flowing through this circuit. Now you might have noticed something a little funny if you haven't thought about this yet, but you'll notice my current direction is in the opposite direction that the electrons would flow. Electrons flow from negative to positive, but current is defined as flowing from positive side of the battery to the negative. As an electron moves this way, it's going to leave behind a positive empty spot. So as electrons move to your left, then the positive spots move to your right. And I is the current is the flow of those positive charges. I guess my cat was flowing from one side of the screen to the other there. Okay, so I'm gonna save this one for last. Okay, but I'm gonna go from left to right. Let's do this top part here. So parallel resistors, 1 over Re, or I'll say Rp for those parallel piece up here. My little part 1. We're gonna have 1/10 plus 1/10. All right. These two are not in parallel with anything else in the circuit. 3 ohms and 3 ohms and 3 ohms, these are in parallel with each other, but they're not in parallel with either of these other parts. So we're going to take the circuit one part at a time, one piece. Now you notice when we take 1/10 plus 1/10, we're going to get 2/10. So again, we're back up here. 1/10 plus 1/10 is 2/10. So 1 over Rp is 2 over 10. So we flip that, flip, and we get Rp over 1 is 10 over 2. So look at that. Equivalent resistance of parallel resistors, if they have the same value, we actually end up dividing it by the number of branches of that value. So 10 divided by 2 is 5. Right? So these two together are 5 ohms. Right? Do you see that pattern? 2/10. Now, let's take a look at, there's nothing we need to do with this 2 ohm value here. I'm just going to circle that because we're going to add up all these circled values in the end. And we have a 3, 3, and 3. So let's look at that one. We're going to have for my second part here, part 2, another parallel resistor section. We have 1/3 plus 1/3 plus 1/3. Now, can you guess what this is going to be? Is it going to be half of 3? Is it going to be 1/3? We'll see. So 1/3 plus 1/3 plus 1/3 is 3/9. No, this is 1/3 plus 1/3 plus 1/3 is 3/3. It's actually 1. Okay, so Rp over 1 is still equal to 1 ohm. All right, all those together are 1 ohm. So if we have 3 of the same resistor value in parallel with each other, we're going to take that resistance value and divide it by 3. All right, 3 divided by 3. Here we had that 10 divided by 2 branches. So it's the resistor value divided by the number of branches. Now that only works if you have the same value as the resistor for each of those branches. For our previous example, notice 5 and 10 didn't really come out nice and sweet like that. It came out as a kind of a funky number there, 3.33 was our result. So what I'm talking about is just, if you ever see this, it is a nice shortcut if you've got 2 resistors of the same value in parallel. You just divide by the number of branches. Okay. So now we've got 1, 2, 3 parts of the circuit. Let's look at this fourth one. All right. What happens here? Do we do 1 over 2 plus 1 over 3 plus 1 over 10? Well, it doesn't quite look like this, does it? It's not 3 branches, it's only 2. But how much resistance is on the top branch? In other words, as an electron comes around, some of them, or I should say as electrons come around, some of them will go to the top branch and some will go to the bottom branch. How much resistance does an electron meet up with on the bottom branch? 10 ohms. How much resistance does an electron meet up with on the top branch? Well, 2 and then 3 ohms for a total of 5. So the first thing you want to do in this situation is take 2 plus 3. There's 5 ohms up here, and there's 10 ohms down here. So this is really 5 ohms in parallel with 10 ohms. And we've done that before. We did it right here on this side. Okay. So just to kind of repeat that, 1/5 plus 1/10 is the 1 over RE. 2/10, find the common denominator, plus 1/10 is 3/10. Flip it and we get 3.33 ohms. So over here, all these together are 3.33 ohms. Okay, so there we have it, those 4 pieces, 5, 2, 1, and a 3.33. So our equivalent resistance, kind of step 3 here. All right, fit it on. Can I do it? Well, 5 plus 2 plus 1 plus 3.33. 5 ohms up top, plus 2 ohms, plus 1 ohm, plus 3.33 ohms. Is that last little segment there? Actually, last big bloated segment. Okay, so we get 7, 8 plus 3 more is 11.33 ohms. There it is. Okay, weird, funky circuit. I bet you were like choking when you first saw this, but really when you start working on these, as big as they can get, they're not really all that difficult. You're just going to take them apart one piece at a time and sum up all those results at the end. We're not doing anything, we're just adding here. We're not doing anything overly complicated. No algebra in these steps. We're just doing some at most fraction addition. So let's not forget our last step. V equals IR. We've got 20 volts applied to an equivalent resistance of 11.33. So 20 equals I times 11.33. And calculator off here to the side, 20 divided by 11.33, those cancel. And 11.33. Got a 1.77. I like to ask myself, does this result make sense? In case I plug it in my calculator incorrectly. So this is like a 20 divided by 10 is 2. 20 divided by 11 would be a little less than 2. So there we go. That's a good answer right there. Okay. So these are combination circuits, and your next step is to try out your own. Good luck.